So in mathematics, an arithmetic sequence is essentially for each new term in the sequence, you add a number by the common difference, which is a given number that doesn't change. So basically, let's say you start off with the term with your first term is 2, and each time you're adding 3. So your second term would be 5, your third term would be 8, your fourth term would be 11, and so forth like that. And so essentially, you are just adding a new number each time. And there are two ways to represent this. In the explicit formula, just how you would represent that is an is equal to, so in this example we have is -3, 0, 3, 6, and 9. In an explicit formula, that would be a sub n is equal to -3 plus 3 distributed to n minus 1. And another way to represent this is in the recursive formula, which is u sub 1 is equal to -3, and u sub n is equal to u sub n minus 1 plus 3, where n is greater than or equal to 2. And so the next step of this is a geometric sequence, and that's where you multiply the number by the past term each time. So an example of this would be 4, 8, 16, 32, 64. And the explicit formula of this example would be a sub n is equal to 4 times 2n minus 1. The recursive formula of this would be n sub 1 is equal to 4, u sub n is equal to u sub n minus 1 times 2, where n is greater than or equal to 2. And the next step of this actually is a shifted geometric sequence. So that's where you multiply the number by each term, and then you also add something. You add a number. So an example of a shifted geometric sequence would be 1, 3, 7, 15, 31. The explicit formula of this is a sub n is equal to 1 times 2 to the power of n minus 1 plus 1 distributed over n minus 1. The recursive formula of this particular shifted geometric sequence is u sub 1 is equal to 1. So that's saying the first term is equal to 1. U sub n is equal to u sub n minus 1 times 2 plus 1, where n is greater than or equal to 2. And sequences can be applied very well in real life to find the values of loans and investments. So let's assume that a man, Michael, has just purchased a car valued at $23,000. The car depreciates at a rate of 2.2% monthly. After owning the car for 33 months, what will its value be? So we can see here, A33, that is the number of the term we want to find, the 33rd month. The starting value is $23,000 because that's what he purchased the car at. And the rate that it depreciates is 2.2%. So to find the rate of decay, we have to subtract 2.2% from 100%, which gives us 97.8%. And to put that into a decimal, it's 0.978. And that gives us the rate at which it depreciates. So, and then the next step of this is to see how it's raised to the power of 32. And that is because the way that explicit equations work, to find the 33rd term in this case, you have to actually multiply it to the 32nd power because of the n minus 1 that is present in the explicit formula. And so after you crunch the numbers, the car will be worth $11,286.81 in 33 months. Now let's look at another one. Shelley wants to put $12,000 into an account that gives her 3% interest compounded annually. After 75 years, how much money will be in the account? So again, you start off like this. A75, that is the number of the term that we want to find, is equal to $12,000, which is the starting value, 1.03, which is the rate of growth. You can calculate this because 100% of the money is the 12,000, and then the 3% interest that's working for her is 3% each year, so that you put in 1.03. And because of the n minus 1, you raise that to the 74th power. And once you calculate that, the answer is $106,938.94 will be left in the account in 75 years. There are three forms to express a quadratic function: general form, factored form, and vertex form. So in this example of the graph on the left, the general form of this equation is y is equal to x squared minus 8x plus 16. In factored form, it is expressed as y is equal to x minus 4, x minus 4. In vertex form, the graph on the left is y is equal to x squared minus 4 plus 16. General form, the graph is modeled by the equation ax squared plus bx plus c is equal to y. A is the horizontal or vertical stretch or shrink. If a is greater than 1, then the graph is shrinked horizontally and stretched vertically. If a is greater than 1, then the graph is stretched horizontally and shrinked vertically. B is equal to the number of x terms after expanding factored form of the equation through FOILing, which you may have learned earlier on. C is the y-intercept of the graph. Factored form is modeled by the equation a distributed over x minus h1 sub 1, x minus h sub 2. A is the horizontal or vertical stretch or shrink, and this is the same, the way A works is the same throughout factored form, general form, and vertex form. A stretches or shrinks the graph. H sub 1 and H sub 2 are the zeros of the graph, or where the graph crosses the x-axis. Vertex form is modeled by the equation A distributed over x minus h, squared plus k. A is again the stretch or shrink. H is the axis of symmetry of the graph, or the location of the vertex on the x-axis, and k is the y-intercept of the graph. Stretches and shrinks, so now we are manipulating the graphs. If a is greater than 1, then the graph is shrinked horizontally and stretched vertically. If a is less than 1, then the graph is stretched horizontally and shrinked vertically. And this can be seen well in the graphs of 4x squared, and 1/4 x squared. Now you can see in the green, the graph 4x squared is the stretched graph vertically of x squared. Notice how it increases at a more rapid pace because it's being stretched vertically, but it doesn't expand horizontally as fast because it's under a horizontal shrink, Now, reflection is where you're essentially mirroring the graph over an axis. To flip a graph, make every x in the equation across the x-axis. Make every x in the equation a negative x, and every negative x equal to x. And this can be seen in the graphs of x squared and negative x squared on the top right. To flip a graph across the y-axis, place the zeros on their respective opposite sides of the x-axis. And this can be seen in the graphs of y is equal to x minus 2 squared and y is equal to x plus 2 squared, where y equals x plus 2 is the original graph, and its counterpart across the y-axis is x minus 2 squared. Now, if you want to move a graph up or down vertically, simply add or subtract, respectively, the desired numbers of movement on the y-axis. and this can be seen from the graphs y is equal to x squared, y is equal to x squared plus 3, and y is equal to x squared minus 2. Notice how y equals x squared, the y-intercept is at 0, but with y is equal to x squared plus 3, it moves up 3. In the graphs, y is equal to x squared minus 2, it moves down 2 from y is equal to x squared. This is because the number after the x squared is the y-intercept. Horizontal translation. If you want to move a graph left or right, put the location of the desired 0 into one or both of the x minus h1, x minus h2, or x minus h squared models of a factored form equation. This will translate the graph and change the location of the zeros. This can be seen in the graphs of x squared and x minus 4, x plus 2. Notice how there are zeros at negative 2 and 4, and those were the desired zeros in this case. And it horizontally changes the graphs and shifts it over, and because of this change of the zeros, it actually causes a vertical translation as well. And all of the previous stretches, shrinks, translations, and reflections work on the graphs of these functions: radicals, other conic sections, hyperbola, ellipses, and circles, as well as absolute value and linear equations. To determine the degree of a polynomial, check the number of the times the graph crosses the x-axis, and that number is the degree of the polynomial. That's a general rule. So notice the second degree polynomial, it crosses twice, third degree crosses 3 times, and the fourth degree crosses 4 times. There are many properties in mathematics that can help one determine the way an exponent will work. The first of these functions is the product property of exponents, which means that a raised to m times a raised to n is equal to a raised to the m plus n. The quotient property of exponents is am over an is equal to am a to the m minus a to the n. Definition of negative exponents is a raised to the negative n is equal to 1 over a raised to the n. The zero exponents property is a to the 0 is equal to 1. The power of a power property is a to the m distributed by n is equal to a raised to the m times n. The power of a product property is ab distributed by the raised to the m is equal to a raised to the m b raised to the m. The power property of equality states that if a is equal to b, then a raised to the n is equal to b raised to the n. The common base property of equality states that if a is raised to the n equals a raised to the m, then n is equal to m. Properties of logarithms. A logarithm will produce the value of an exponent. The definition of a logarithm. For a is greater than 0 and b is greater than 0, log base b of a is equal to x is equal to a is equal to b raised to the x. Change of base property for logarithms. Log base b of a is equal to log a divided by log b, where a is greater than 0 and b is greater than 0. The product property of logarithm states that log b mn is equal to log base bm plus log base bn. Quotient property of logarithm states that log b of m over n is equal to log bm minus log bn. The power property of logarithm states that log b m to the p is equal to p times the log of b base b of m. The logarithm property of equality states that if log b base b to m is equal to log b of n, then m is equal to n. The law of sines states that the sine of angle A in the triangle is equal to the length of side A. This works for B and B, as well as C and C. And in a right triangle, the sine is equal to the opposite over the hypotenuse of the given measure. The law of cosines explains the length measures of triangles. So c squared is equal to a squared plus b squared minus 2ab of the cosine of c. And in a right triangle, cosine is adjacent over hypotenuse. Tangent rule. In a right triangle, the tangent is the opposite over the adjacent of theta. In probability, tree diagrams are especially helpful to explain the probabilities of hypothetical and real-world occurrences. And to find out a path's probability, you simply multiply it. So as seen on the model shown, your chance of throwing two heads in a row is 0.5 times 0.5, which is 0.25 or 25%. And they can be especially helpful for determining probability. Factorials. The product of an integer and all the integers below it, and it's represented by an x with an exclamation point after it. Example, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, or 720. And it's useful for finding the probability of an event, especially in a permutation. In a combination, so in probability, the combination is a selection of items in an order that doesn't matter. Example, a fruit salad is a combination of watermelon, pineapple, and grapes. So essentially the order doesn't matter in which the ingredients go in the fruit salad as long as they're there. And then is represented by the n sub n, c sub r. N is the group being selected from, and C will tell us that it's a combination rather than a permutation, and R tells us how many we are taking from the group. An example of this would be how many different committees of 4 students can be chosen from a group of 15. There are 15 for possible combinations of 4 students from a set of 15. So what you do is 15 factorial over 4 factorial, 11 factorial, and that given number will give you the fraction simplifies to 1,365, which means there are 1,365 different possible committees. In a permutation, a group of objects selected has to be in a certain order. So an example of this would be an order of 3 ice cream scoops and an ice cream cone randomly selected from 12 ice cream flavors. And you're looking at not only the combination but the order. So n, it's represented by sub n, p sub r. N will tell us the group of objects selected from, so the number of the objects available. P tells us that it's a permutation and not a combination. And R will tell us the number of objects we are selecting from the group. An ellipse is represented by the equation x minus h squared over 2a2, h is a squared, y minus k squared over b squared is equal to 1. H is the location on the x-axis of the center of the ellipse. K is the location on the y-axis of the center of the ellipse. A is the length of the major axis, and B is the length of the minor axis. The focus of the ellipse is calculated through the equation c squared is equal to a squared plus b squared. And now the example on the bottom right, that is the graph of the equation x minus 2 squared over 16 plus y plus 1 squared over 25 is equal to 1. Hyperbolas are represented by the equations x squared over a squared minus y squared over b squared is equal to 1. That would have it cut across the horizontal axis. And for it to cut across the vertical axis, it would be y squared over b squared minus x squared over a squared is equal to 1. And a is the length away from 0, 0 on the x-axis. B is the length away from 0, 0 on the y-axis. And the focus is calculated by the equation of c squared is equal to a squared minus b squared. And that is a mistake I made on the slide. It's a squared minus b squared. Now, an example of this would be x minus 2 squared over 16 minus y plus 1 squared over 25 is equal to 1. And that is the graph of it on the bottom right. An arithmetic series is a finite sum of terms from an arithmetic sequence, and it is represented by the picture on the right, and it has many real-life applications tied to it, such as calculating the number of births in a country or population growth. The signal notation means the sum of. So the big Greek symbol that looks like an E. And once you plug in the values from your sequence, you can just calculate it right up, and it's very easy. And so that is my review video. Thank you very much for watching, and it was a pleasure doing this. Thank you.